Hello YouTubers and fellow hams. I've got a kit to build. This is the Cricket 40. It is a low power 700 milliwatt CW transceiver, similar to the Pixie but better, designed by David Kripe NM0S with the 4-state QRP group. This little radio is 40 meters. It comes with 2 crystals. It is a direct conversion receiver, so it'll be quite wide. Probably more than a 10 kilohertz bandwidth on receive, which will, well, I got something I'm gonna do about that later. But first, we're just gonna build the kit. It's a single board, and one clever thing that he did on this PC board, as you can see already, is there's no toroids to wind because the inductors, the 3 inductors in the circuit, are actually created using spiral PC board traces to make the inductors right on the PC board. That's pretty cool. It'll make it a little bit quicker to assemble. You won't have to wind toroids. How about that? It's all through-hole design, no surface mount chips, real simple circuit. We'll look at the schematic of it in a moment. It's a nicely done PC board, double-sided, with ample pads, and the veneers that go through look nicely plated down through there. Nice job on the board. And these parts over here come off and mount here to form a key right on the board. So you'll have a built-in key. It runs off a 9-volt battery, which will sit here. I'm probably going to eventually adapt it to also run off 12 volts, but that's down the road. I've got some modification plans for this after I build it. But first off, we're going to build it. Now over, it's off camera, you can't see it, but over here I've got my tablet. The manual is a PDF. I don't have a printer here in the RV, so I'm just going to work off my tablet for the manual as I build the kit. So I'm going to get all the parts out here and do a parts count and make sure I've got all the parts and components, and then we're going to start building it. And while I'm doing that, my doppelganger will take you through the schematic, and we'll look at how the little radio works. So let's get busy. This is the schematic of the Cricket, and it's a simplicity itself. It's a very simple design. It's not going to be a high-performance radio for a couple of reasons we might touch on, but let's look at it here at the basics. Okay, so down here we have the crystal oscillator. This is the heart of the radio, and it's a simple Colpitts oscillator using Q1 here, and our crystal is right there. So a simple Colpitts oscillator. There's an interesting little bit right here, the transmit-receive offset, and what he's doing is from the crystal, when this transistor is off, the path goes through this capacitor, and that capacitor, 39 picofarads, shifts the frequency of the crystal a bit. So about 6 to 700 hertz, somewhere in there, it'll shift. And then when we key down, this transistor turns on, and the path then becomes like that, bypassing that capacitor, and we shift up to the crystal's frequency. So that's how he does his transmit offset. Pretty simple. I got to email him. I'm curious about what D2 and D3 are doing here. They're 2 reverse biased diodes, one from the plus 9-volt power rail and one to the ground. But they're reverse biased, so I don't know what they're doing. The only guess that I have is that perhaps they're somehow making the oscillator more stable. The antenna path comes in here to the mixer, right? So AM broadcast signals that might be coming down the antenna that are quite strong could come in that way. And perhaps these diodes will clamp off those higher voltage, RF voltage signals, perhaps. I don't know. I'm going to email him and ask about those. But anyway, that's the oscillator. Now, if we zoom out a little bit, we see that the oscillator feeds Q2, and when we're in receive mode, signals from the antenna come in through the low-pass filter into the mixer, and the oscillator comes in from this direction into the mixer. And with a mixer, the output here will contain both the oscillator's frequency, signals that are coming in from the antenna, and their sum and difference. So the frequencies added together and the frequencies subtracted from each other. So the way a direct conversion receiver works is, let's say we're oscillating at 70-30, and there's a signal coming in at 70-31, a CW signal. What's going to come out of that mixer is going to be the RF, obviously, from both sides. But it's also going to be the sum, 70-30 plus 70-31, so 14.061, and the difference, which would in this case be 1 kilohertz. Now this choke here is going to choke off most of the RF, right? So what's going to end up getting past that choke would, in the case we just mentioned, would be the 1 kilohertz signal, the CW signal. So that would then proceed up here to Q4, which is acting as a detector and a preamplifier. So it's going to detect that 1 kilohertz signal, rectify it into an audio signal, and then amplify it and send it on up to the audio amplifier, right? And also we have a diode here to the key. So when the key is grounded, it grounds this transistor and basically mutes it. So the receiver side, the audio section, is muted when we key down to transmit. R4, make a note of that. R4 is the resistor that couples that audio up into the audio amplifier. And we'll talk about that when we're doing the assembly. I have a plan there for R4. Okay, the audio amplifier chip here. And here's our 9-volt battery coming in, by the way, with some filtering here to filter RF out through the power switch up here. The audio amplifier drives the earphones. Now, this is something that puzzles me at first when I first looked at this. Usually with an audio amplifier, you're going to have the high side, and then you're going to have ground out here. And if you have a stereo jack, you'd send that audio to both the left and right ear speakers. But what he's doing here is the audio is, it's got two outputs on pin 8 and pin 5 over here, right? Sort of a high and a low side. And what he's doing here is, if I'm reading this right, okay, on the jack, pins 1 and 2 are the high side to the left and right speakers in the earphones. So they share a common, which would normally go to ground, but it's not going to ground down here. It's going to the side tone oscillator. So what's happening is the audio's from the high side is coming out, and it's going through one speaker, and that speaker is then tied through the common that would normally go to ground, right? It would normally go to there. That speaker is then tied to the other speaker, which is going to here. So he's looping the audio through the left and right earpieces, sharing their common ground. And then their ground, he's feeding with the side tone oscillator. So that's quite clever, but that also makes it very difficult for me to tap the audio off of this guy to give you a sample of what it sounds like. So I'll have to figure something out for that. The side tone oscillator here is 2 transistors set up like a multi-vibrator. It's an old circuit that we used to, well, I remember encountering that circuit on an old Radio Shack Electronics project kit, and it was a light bulb flasher. And basically what happens is we've got a capacitor here, right? And we got a resistor where that capacitor, well, where is that? We got a resistor up here that can bleed that capacitor off. So one transistor turns on and charges the capacitor. And then when the other transistor turns on, it discharges the capacitor through to ground, okay? And when that capacitor is discharged, then the base of this transistor turns this transistor back on, which turns this transistor off, and the capacitor charges back up. So it just goes back and forth and back and forth and back and forth. And the time that it takes for this capacitor to charge and then discharge through that resistor will determine the interval between when one transistor turns on and the other turns off, and then vice versa. So that capacitor plus this resistor for discharging will create an interval, and that interval then is the sort of the frequency of the side tone, which is tapped off of this transistor here through R9 to the ground side of the earphones, where it'll then ping through both elements of the earphones, finding a return path somewhere through this chip or its associated circuitry. So that's how he does his side tone, real simple. When you're in transmit mode, okay, here's their keying circuit, right? And our keying circuit activates this transistor, which actually does the current handling of the keying. So when we key this down, let's see, this transistor is a PNP, so by default it's conducting, but we also have a 9-volt signal here bias to turn the transistor on, which would stop it from conducting. And when you key down, that draws the base down to 0 volts. The transistor turns back on, and we get 9 volts down this rail. The 9 volts turns on the side tone oscillator here. It does some things over here. Well, let's see, that resistor goes down. Yeah, that's the offset, so it turns on the offset. It provides power to the power amplifier here so that it will amplify the oscillator's output, and then that gets driven back up the antenna that way. So keying, real simple. So this is a direct conversion receiver. There is no RF preamplification on the antenna path coming in, so it's not going to be very sensitive. Signals are going to be kind of quiet unless they're strong and local. Oscillator leakage is another problem with direct conversion receivers. This mixer here, when we're in receive mode, some of that oscillator signal is going to leak through the mixer back out the antenna, right? So that's a problem with direct conversion receivers. You'll always get some oscillator leakage. It won't be very much power leaking out from the oscillator, probably a few milliwatts. We might actually try to measure that. But with a direct conversion receiver, if there's any other radios in the vicinity, they will hear your oscillator frequency when you're in receive mode. It'll leak through. So that's a problem with direct conversion receivers. I remember being at field day when I was young and taking my HW8 there, which was also a direct conversion receiver. And some of the other hams there asked me to switch radios because they could hear my oscillator, my local oscillator, and it was bothering them. So I had to not use my HW8 at field day. I suspect in this case it'll be quite a bit of leakage coming through from the oscillator out the antenna. But that's just part of a direct conversion receiver. So this thing is really, really simple. It's not going to be a high performance radio by any means, but it's a fascinating little radio. Okay, let's get back to the assembly. So the first step was snapping off the PC board parts and assembling the knob. Big deal. But the first step is actually the battery terminals, and he has an instruction that is a trick that I like to use myself when I'm building kits that have a connector or something that is going to have a mating surface or two-part connector. Like if you had an edge connector and a pin header that it was going to, I will partially assemble things so that the two are connected and mounted the way that they're going to be mounted before I do any soldering. That way they all line up, and he wants the same thing done here with the battery. So plus side over here, plus side marked on the board. I put the battery terminals on the battery and insert them into the board to make sure everything is lined up, you see. So the battery is there, that's how it's going to line up. I'm going to turn that over, and then with the battery on there, I'll do a little soldering to lock the solder the pins on. I've got my soldering iron down to 600 degrees. I like to run it a little bit cooler when I'm working with PC boards so I don't melt the traces off the board or lift the pads. And these points need to have adequate solder. Got to get it to flow through the veneer. Make sure I got a nice little pyramid of solder there. I don't have a good camera to give you a close-up. I wish I did. Maybe I can zoom in on the video and get an adequate signal. But these are going to have mechanical strains on them as you're hooking up and unhooking a battery. So we want to make sure we get these solder pads nice and covered and the solder flowing through the veneer, so we got plenty of strength there. There we go. Nope, need some more solder on that one. Now I can remove the battery, and voila, they're lined up. How about that? So that's a trick, you know. Obviously there was no components on the board, so there was no worries about power from the battery going anywhere or doing anything. Remove the battery and proceed. The next step is resistors. And yeah, we got a bunch of resistors. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 resistors and 1 inductor. So yeah, I'm going to get started on the resistors. Now I've got my multimeter here, and I'm going to double check each resistor's value before I install it. And I also need to take a look at the schematic, because there's one resistor that I'm going to do slightly differently from the others. Orange, orange, black. This would be the inductor, yep. The resistors are all 1/8 watt carbon resistors. But there's one thing that looks like a resistor. It's green, it's a little bit bigger. This is actually an inductor, L4. So I'm going to go ahead and install that first, so I don't get it mixed up with the resistors. L4, where are you? The board is nicely labeled. Each part number is present and clear. There's L4 right there. I bent the legs, and I'm going to insert it into the board flush, like so. And it should hold itself while I solder it. There we go. And we'll clip the leads off, and we'll go on to the next resistor, or we'll go on to the resistors. And as I said, I'm going to verify each resistor's value with my meter before I solder it in, before I install it. I just like to be a little extra sure. I don't trust my old eyes these days. The other thing I do when I clip these leads off is I'll put my finger on the tip of the lead so it doesn't go flying. See? If you don't do that and you just clip it, they go flying, and they can be hard to find, or if they fly into an open eye, they can hurt. So that's a little something I do. Hopefully I can keep all this in shot. So there we go. The first component is on. Get this angled right so you can see that. There we are. And now I just have a bunch of resistors to do. R1, 470 ohms. That would be yellow, purple, or violet. Brown, it's the only 470 ohm resistor. Where did I put that guy? Here it is. Yeah, that's yellow, violet, brown. Okay, to the multimeter. This should be 470 ohms. Yeah, 458. That's within tolerance. And that is R1. R1. There you are, over here in the oscillator. And again, we'll take it down flush to the board. Now in this case, the leads didn't grab too well, so I am going to put a slight outward bend. I pull as I move outward to bend these so that they bend at the board, and then that will hold the resistor on there while I solder it. There, we'll do that. Then it might be in focus. Again, I'm holding on to the lead as I clip it so it doesn't go flying. Okay, I'll get the rest of these resistors done and then we'll come back and do the next step. All right, I have finished the resistors. They're all on. Now I did something a little tricky here, and hopefully you can see that right there. You see that resistor? That is R4. And I might have mentioned when I looked at the schematic for you that that is the resistor that audio comes through from the receiver to the audio amplifier. And what I've done is I've stood it up so that this line here, this wire that's extended, that's the high side that goes to the audio amplifier. So that's the audio signal from the receiver to the audio amp. Can you guess why I did that? Well, if you're guessing filtering, you might be right. I plan on modifying this kit with a narrow CW filter. And in order to do that, I'll need to insert it into the audio path before the audio amplifier, which will be that lead on that resistor. So I'm thinking ahead here. That'll make that much easier for me when I go to patch in the audio amplifier, or the audio filter, I should say, the CW filter that I'm going to use. So I got the resistors all done. Next up are the transistors. And most of these are 2N7000s. I'm going to need my magnifying lens. Even with my good glasses on, I can't read those numbers. Well, maybe I just can. Yeah, 7,000. I guess there's only one that's different, so I can separate it out ahead of time. But we'll do Q1 first. Q4. I need my needle nose pliers. So the legs on these are stood out sideways. Sometimes they stand them out on circuits in a sort of a tripod fashion. But I'm going to just put a little outward bend on those leads. There, you can kind of see how I did that. And then we just have to, he's got them silk screened on the board with a flat side and then a little angle and another little angle to dictate the rounded side of the transistor. Because if you look at a transistor, it's got a flat side over here and then it's rounded. So you want to make sure you get the orientation right. So this is Q1. He goes right there. Now my dad, when I was younger, and we built a lot of Heathkit kits, he used to do this. He would stand the transistors way up off the board, like that. And his reasoning, which I learned later was wrong, was cooling. He thought that they would run cooler if they had more airflow around them. The problem with doing that, though, is twofold. Firstly, mechanical. If something hits the board and pushes that transistor, it could twist the legs and they could short, you know. And the other thing is, especially in RF circuitry, parasitic capacitance between the legs. Those long legs running parallel like that are going to have a very small amount of capacitance. And in RF circuitry, that could be a problem. So you want to make sure that you get that down fairly close to the board. You know, about like that. And there you go. You can see how far down I got that. You don't want to put too much stress on the legs. You don't want to bend them out at 90-degree angles to get it right on the board. But get it down there like so. And again, I'm gonna hold the transistor nice and neat while I come down here, and I just put a little outward bend on these component leads so it'll hold itself in place while I solder it. And with transistors, I'll give it a moment like that to cool off before I solder the next leg. And I'll give it a moment again to cool off before I solder the next leg. Don't want to get it too hot. There we go. 1 down, 7 to go. Yeah. All right, I'll get these semiconductors done, and then we'll come back and we'll look at the board before we do the next step, which I think will be capacitors. All right, the transistors are all mounted. And now I've got 3 diodes to do, and these are 1N914s, little switching diodes here. They're tiny, little glass cases. Now on these, you might be tempted to just take your finger and bend the wire over, but I have broken the glass case on one of these before. So what I do is I'll get my small needle nose pliers and I'll grab the pin right next to the glass case like that. And then I'll use my finger to bend the wire over. And then we'll do it on the other side too. And that way I'm bending the wire against the pliers instead of against the glass. There we go. All ready to install. Let's see, this is D1. D1's over here next to the audio amplifier right there. Now, diodes, of course, have a banded end. The band is the corresponds to a band in the graphic on the PC board. He's got a little banded end on the silk screen there, so you can't screw up. Well, I guess you could still screw up, but if you're paying attention, you won't. And I'll get the diode right down on the board, and again, I'm just going to pull out and bend these leads back a little bit so it'll hold itself in there, like so, before I solder. And soldering, I get a little fresh solder on the tip of the iron. I'll clean it on the pad, and then I'll get a little fresh tip on there so I've got a good heat transfer, molten metal to molten metal. And then I'll put the soldering iron on one side of the pin and touch the other side with the solder, and it just flows. It just goes right in. And then I lift the soldering iron tip straight up along the lead, and that draws any excess solder up onto the pin instead of letting it blob around the connector, or around the pad, I should say. So we get a nice clean result. Okay, I've got just a few more diodes to do, and then the IC. And the IC socket, we've talked about that before. I see a problem. I see a problem, I think. We have a 1, 2, 3, 4 pin IC and a 1, 2, 3 pin socket. Unless the socket is meant for something else. I'll have to dig through the manual and see. I don't know if the socket would be for the crystals. I mean, the pins line up. Maybe he wants you to use the socket for the crystals. All right, I gotta look ahead in the manual and see what's going on. But I think perhaps they goofed and sent me a 3-pin socket. Go figure. All right, well, anyway, I'm going to get the diodes and the IC done, and then I'll be back with you. Now I'm up to doing the capacitors. These are tiny. I could barely see the numbers on there, even with a magnifying lens. It's a 103, so this is a 0.01 microfarad ceramic disc. Fortunately, in his manual, he has ample notes on the capacitors. He has the part numbers that are going to be printed on the parts. He has notes about lead spacing on a couple of them, but he also says what type they are. So ceramic disc, monolithic, which are those little gumdrop looking things where The goo is just sort of, it's kind of fat. See that? I don't know if you can see that. Ceramic disc obviously looks like a little disc. Round, flatter. Electrolytic. That's an electrolytic capacitor. Looks like a barrel. Sometimes the leads come out of the ends. So he does give you some clues there as far as the capacitor types. And you can also, if you're not sure, sometimes you can verify by the type and the number of them. For example, there are 3 ceramic discs that are 103. Well, I've got 3 of these smaller ones that I'm pretty sure says 103 on it. Like I said, I had to look at it through a lens. But I've got 3 of those, and they're ceramic discs, so that makes sense. And then there are 2 ceramic discs that should have part number 104 that are 0.1s. And these were easier to read. The 104 is clearer, but they are ceramic discs. So sometimes you can correlate on the parts list if it's got enough information to make sure you got the right capacitors. And these guys are tiny. Okay, so this one is C2, which goes right up here next to the inductor. The ceramic disc caps are not polarized. Doesn't matter which way you put them in. If they're in a crowd of parts, like an area that's busy like this, it might be useful to place them with the numbers facing out in case you have to debug things later. It'll be easier to just see the number on the side of the capacitor, and if it's up against another component, you know, you can't see the other side of it, put the number on the side that'll be clear. That can save you some time later if something doesn't work and you need to double check and go through it and find where the mistake was made. So there's another tip for you. All right, I've got a bunch of capacitors to do, and I think that's going to get all the discrete through-hole components. By the way, on the integrated circuit, which is an audio amplifier, come on, take solder, you silly pad. There we go. I think they sent me the wrong socket. They sent me a 3-pin socket for a 4-pin IC. So I looked and I didn't have any 4-pin sockets handy, so I just went ahead and put the IC directly on the board. It's an audio amp. I doubt I'll have to replace that. But if I do, this is a through-hole board with nice wide pads and veneers, so I should be able to suck the solder out with a solder braid if I need to. Okay, so I got to get the rest of these capacitors done. What's next? Final assembly, which is just switches and connectors. So I get these capacitors done, we'll be getting close to being ready to test it already. How about that? And I got quite a few capacitors to do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 capacitors. And I hate capacitors. My old eyes, even with my thick glasses on and a magnifying lens, I have a hard time seeing the numbers, but we'll make sure to get the right ones in the right places. All right, I'll be back with you for final assembly. All right, the capacitors are done. I hate doing capacitors, especially these tiny, teeny, little bitty ones. So the board has all the small components installed now. What we're left with are jacks, switches, crystal, and assembling the key. On the capacitors, hopefully your eyes are good. I had my thick glasses on, and even with my thick glasses, I still needed my magnifying lens to make sure I had the right capacitors in the right spots, because the numbers are teeny, teeny, tiny on those things. Okay, we're up to final assembly. So next up is the BNC connector for the antenna jack, and it is solder mount. It goes right here. Now it has 3 ground tabs and a center pin right there. 1, 2, 3, 4. So we got to line the center pin up in the hole first, and then guide the other tabs in. And I want to make sure it stays flush, so again, I'm going to solder one of the tabs. In fact, I'm going to boost my soldering iron temperature a bit here. Back up to 700 Fahrenheit. because these big tabs are going to need a little extra heat. And the switch, which is next, and something over there. What's there? Oh, the headphone jack, yeah. Those all have big solder pads, big pins, so you need to make sure that you have enough heat. So I'm going to first solder one of these tabs, just enough to hold it. Okay, and we'll make sure that we're flush. Yeah, I'm flush on the board, so I can go ahead and complete soldering this. All right, so we'll get the center pin first. Yeah, it's going to take a little extra solder too. There we go. Now I can get the tabs. Now the tabs, I want to make sure I get solder all the way around this pad, because the strength that holds the connector in place is the solder on these ground tabs. There we go. Yeah, see, I needed the extra heat. This Hakko soldering iron has been just fantastic. Thanks again to Terry. He sent this to me a few years back. I have used the heck out of it and greatly appreciate it. On those tabs too, I soldered from one side of the tab, and then after I got enough solder on there, I brought the iron over to the other side of the tab to make sure that the solder uniformly joined on the pad all the way around, so you have a nice complete strong pad there, because like I said, that solder is what's holding that connector in place, and there's going to be some strain and stress on that as you fiddle around with it. Okay, the power switch is next, and no polarity there, it just goes straight on. And yeah, it's going to want to stand off, so I need to figure out some way of keeping it up there. I guess I could tape it, but I think what I'll do is I'll just tack solder the center pin. I'll just get some excess solder on my iron and bring that blob of solder over, and we'll just coax it onto that pin and pad. And then I can heat that, and I can straighten out the switch, make sure it's flush. Yeah, that's mostly straight. Slight angle, maybe a half a degree. I'm not worried about that. And I'll solder the other two pins. Okay. The switch, headphone jack. We have two jacks, and they are identical. Okay. Why do we have two jacks? We only have one place to put one. I guess I got a spare jack. Thanks to the kidder for accidentally sending me an extra headphone jack. I'm sure I'll find a use for that in the future. And again, the headphone jack, what's going to be holding it in place are the solder connections. So I'm going to get one of the pins started here. And then I'm going to make sure the jack is flush on the board. I'm going to push down on the jack. This is what I'm going to do is I'm going to use my finger to push the jack against the board while I reheat that solder pad. And I could feel it move just a slight bit in. Now it is flush against the board, and I can solder the other pins and finish soldering that pin. So get a nice clean installation here. And again, I need to make sure that the solder goes all the way around that pin and that pad, because the strength that holds that jack in place is the solder. That's the physical mount, the mechanical mount that's holding it on there. There we go. Actually, I don't have a pyramid on that one. Solder flowed down into the veneer, the plated channel between the two sides of the board. So I can add a little more. Oh, and this one too, I didn't get quite a nice, there we go. There, now I got a nice pyramid shape where the solder comes up around the pins. So there's the headphone jack. Okay. Locate the 6-pin dip socket. Using diagonal cutters, snip it in half to make 2 3-pin sockets. Use diagonal cutters to clean up the broken face of the half socket. Snip off the center lead of the socket flush to the plastic body. Solder the socket onto the board. Oh, for the crystal. Ah, that's what this is for. They want snip it in half. Okay, so they want me to take this and turn it into a 2-pin socket for the crystal by cutting it in half. There we go. And then cleaning off the little plastic stubs that are on this side of it. And then snip off the center lead. There. So we've now got a 2-pin socket for the crystal socket. And yeah, solder it into the crystal position. Okay. I may eventually, I'm going to have to do the same thing here. I'm going to have to get some solder on my iron and get one of the pins, because this doesn't really want to stay flush against the board. I may end up desoldering this for another modification I'm going to make to this guy. See, my plan is it there? Okay, now are we flush? Not quite. I'm eventually going to build this kit into an enclosure and make it like the old Paracet spy radios. And one of the things I want to do is I want to make it switchable with 2 crystals. It came with 2. One is 7030 and the other is 7122. 2 popular frequencies for low power. All right. Now we're going to assemble the key. So the electronic part is done. I can turn off my solder station. So now we need the screws, spacers, washers, nuts, and we're going to assemble the key. Locate the 6/32 screws, spacers, and hex nuts. Assemble the key into the board by passing the screws through the top of the key assembly using spacers between the key and the PC board. So I wonder what all this was about. Since that's just extra stuff, where'd I put the key? Here it is. Okay, so we put screws through from the top of the key to the top of the key, spacers between the key and the PC board, nuts on the bottom side, and tighten with a screwdriver. What about the washers? Obviously we want the screws to make contact. I don't know, I might use the washers on the bottom of the board. So we'll put, oh, the spacers thread on? Yep, spacers thread on. Where's my screwdriver? That's a tight fit. Need a tighter grip on that spacer. It was just spinning in my fingers. Okay, the other screw. The spacers are a tight fit. Okay, and they go through there. Do we have enough space for the washers? And then the nuts. I guess so. Threads almost come all the way through. We'll tighten that down. I might have to leave the washers out. Might be why he doesn't call for them. No, that held. And there's our key. Clever. Very clever. Look at that. It just clears. Not a lot of action there. I might put the washers in actually above where the spacers are to introduce a little more of a gap. Because that's just too close. That is too close. So what I think I'm going to do is I'm going to loosen these up. I'm going to take the nuts off. And I'm going to put the washers under here. Maybe that's what he included them for, and he just didn't put that in the instructions. All right, now we'll put the nuts on. Yeah. I guess it's to taste. I like that little bit extra travel there, so I think that's the way I'm going to leave it. All right, so there's the key, and we're done. This little extra piece in between looks like it had an ulterior motive. Maybe that's a... Oh, I know what that is. That's a keying adapter. That's what the other plug is for. Okay, you can put this on there with the other headphone jack, and if you hook that up on here, yeah, that would probably the screw from the knob goes through there to make contact, and then that would allow you to connect a external keyer. So extra parts. Final bit is rubber feet. It comes with little rubber feet. Look at that. So these go on the corners of the board. Which I'll probably eventually drill screw holes there to mount this in an enclosure. And there is our completed cricket. Well, we've only got one thing left to do. Let's hook it up and see if it works. So I'll need an antenna. And right now this is connected to my doublet through the antenna tuner. And we're going to need audio. Obviously it's designed to go with headphones, but it'll also work with a small speaker. And I have a big speaker amplifier, so I'm going to plug that in. We'll put the battery on it. I think we're ready to hit the switch. Woo! That side tone's loud. Oh, you know what? Crystal! It's like, why don't we hear anything? Okay. I bet it'll work now. I hear noise. Okay, the antenna tuner can't tune it. So let me get the antenna tuned for 40 meters. Not enough power coming out of it for the LDG tuner, which should handle tuning with 1/2 watt. But then again, I don't know the condition of this battery. Okay. The antenna is tuned. One thing I don't like already is that the side tone oscillator is way louder than the receiver. Okay, you can't hear that. Yeah, there's just not a lot of audio there. I can hear some CW. I can hear stations in the background. Yeah, so it is working. All right, I'm going to have to get reconfigured for a demo here. So let me play with it a little bit, get things sorted out and ready to demonstrate it, and we'll show you how it operates. All right, I have the Cricket hooked up to my doublet antenna, and I'm listening in the headphones, and I can hear several stations, and I can hear a broadcast radio station very faintly in the background. So I have tried different ways to capture audio using the built-in headphone jack, but as we saw from the schematic, the way he's driving that is really kind of odd, and I'm not getting a good tap. So what I'm going to try is, I'm just going to take my lav mic here that I'm talking on, sorry for the noise, and we're just going to stick it right in the headphones. So hopefully you heard that okay. I'll take that particular chunk of audio and enhance it in Audacity, bring its volume up so you can hear it a little bit better. But it's not a very sensitive receiver. But then again, we've got no RF preamplifier on the antenna input. We don't have an IF section, which would normally present several stages of amplification and filtering. You know, it's a simple direct conversion receiver, so signals are down a bit, but you can hear them in the headphones just fine. So I'm going to go ahead and play around with it some and try to make a few contacts, and in a future video I'll let you know if I've made any contacts on the Cricket. But with 1/2 watt out, as we've now measured, it certainly should be possible. So I hope you all enjoyed that, and we'll see you in the next video. Thanks for watching. If you enjoyed the video, don't forget to give it a thumbs up. Also, if you're not already a subscriber, click to subscribe. Join us on the Facebook channel for discussion about the videos. And if you'd like to help support this channel, please click to support me on my Patreon page.